Hi everyone. So this is a work that I did last year with Julien Audifrin, who was at the time at the CMLA, and all the other affiliations are mine. So for those of you who are not French, it's possible to have 6 different affiliations. So I'm going to talk to you about Bandits problem. In particular, I'm going to talk to you about a problem of Bandits where you cannot compare the items that you're going to work on. And in order to illustrate the thing that I'm going to talk to you about, I'm going to talk to you about movie recommendation. Very important part of my talk is just the first part, where I'm going to set the problem. So if you can understand the problem, it's nice. Afterwards, it's going to be a bit technical, but it's just one slide. And after that, there's going to be some experiments, and so it's two slides. But the very important part is the first part. The thing that we are interested in is given a set of items. Here, the items that we're going to work with is a set of movies, and we want to recommend to a user the best movie, the movies that he or she can be interested in. So there are a lot of different problems of recommendation that you can think of. Like when you go to Amazon and you want a product, or if you go to, I don't know, any Zalando, if you want to buy clothes, then you're very happy with the system if it's able to provide you with some recommendations that fit your tastes. The thing is that one way to cast a problem of recommendation is to use the bandit problems. So I think that you already had a talk on bandits this morning, but even though you had that and maybe you're all familiar with the problem, I'm going to go back on the problems just a little bit. So bandits problem are inspired by the multi-arm bandits that you have in casinos, where you put some money and you pull an arm and you want to have as much as money as possible. So it's been used for different kinds of problems, like this problem, where here you can actually see the problem of a recommendation as a bandit problem, because it's an online problem. You receive the information of the fact that this movie is good or is bad one at a time. So it's an online problem, and your system has to adapt to all the information it collects during the time it runs. And the thing that the system wants is to minimize. So it's a technical term, but don't care about it. It wants to minimize the regret, meaning that it wants to minimize the number of times it proposes to users bad movies or bad products. A model for that, an actual model. It's a very, very, very basic model. Is the model of multi-arm bandits, where you have different machines, and the thing that you want is to lose as less money as possible. I'm not going to say to win as much money as possible, because it's very difficult to win. And then you have this problem of given a set of arms, to identify between all the arms that you have in front of you, the one that is going to provide you with the highest gains. And you have to do that very quickly. You cannot use your money just to explore, to see what is the best machine, but you want to use your money as efficiently as possible, so that at the end of the day you have as much money as possible. But the thing is, we humans are very bad for giving scores. For instance, in the problem of rating movies, I can put 5 stars for a movie that I like as much as you do, and you might put 3 stars, because that's the way you rate things. So we're not very, very, very good at rating things. All the more so when we are required to provide absolute values. So it's not very easy to say that this movie is 5-star or 4-star or 2-star. However, we are very good at saying that I prefer this movie over this other one. And it's not that we're very good, but we're very more comfortable with the task of comparing things than giving absolute rates. So This brings us, if we have in mind the problem that I mentioned just before, to say that we're not going to, if we want to cast the problem of a movie recommendation as a bandit problem, we're not going to use the usual framework, but instead of that, we're gonna try to compare movies, meaning that at each time, when you want to have some feedback from a user, we're gonna provide him or present him with 2 different movies, and he's going to select the one that he prefers. So that is one way of collecting information on the movies, which is more in line with the abilities of humans to compare things instead of providing absolute rates. So this brings us to a new problem, which is almost the same problem as the multi-arm bandit, where you had to pull 1 arm at a time. Here, you're going to pull 2 arms at a time. And each time you pull a pair of arms, the system or the user is going to tell you, this arm is better than the other one. So this, again, is a framework that is more, that humans are more comfortable with, because it's more a comparison-based process. And there are a lot of different algorithms that exist that were tailored to tackle the problem of what is called dueling bandits. The problem or the shortcomings of the classical settings is that usually you suppose or you assume that all the items that you're going to work on or that the system wants to recommend to you are all comparable. However, it's not always the case. For instance, here, and I just stay in the realm of movies, we have 2 different movies which are from different genres. The first one is a comedy, the second one is adventure, and it's not, it doesn't make sense at all to compare those two movies. So it means that in the case of dueling bandits, the hypothesis or the assumption that is made is that all the products, all the pair of products are comparable to each other. In fact, if you look at real-world applications, it often happens that the products cannot be compared. And this, what we are interested in, actually, is the problem of doing dueling bandits on what is called partially ordered sets. So partially ordered sets are almost a set that you're very familiar with, except that there are pairs of items that you cannot compare. You can say that this one is larger than that one, or that other one is smaller than the other one. And it pertains to something that maybe you're familiar with. The thing is something from economics that is called the Pareto front, or multi-objective optimization, where you have different data that you want to work with, but they are not comparable. Imagine just data that are represented as vectors, then you cannot compare 2 vectors. Actually, you can do it if component-wise, if all the component of the first vector are lesser than the second vector, then you can say that one vector is larger than the other one. Otherwise, if there is a mix between the larger and smaller, then you cannot say anything. And this is something that is very frequent, and actually this is something that companies work on. For instance, if you look at phone companies, when they provide you with mobile plans, then you cannot compare. You cannot compare an offer made by SFR, by Bouygues, and by Orange. It's not possible to compare them. Or Free. Sorry, Free. You cannot compare them. So it's very frequent to have to deal with sets where you cannot compare everything. All right. So my problem here. So this is the first part that you all had to understand. Was I'm interested in a problem where I'm going to do recommendation on items that has the property, the set, the collection of items I work on, as a property that some of the items cannot be compared. Okay, that's the only thing that you have to remember. The second thing is we're gonna use a bandit algorithm to do that. And okay, I'm doing a flash forward so that you know what I'm getting at. At the end, I'm just going to propose an algorithm, a bandit algorithm that is able to do that, to identify what is called the dominant arms. And to do that, we're gonna adapt. It's not gonna be very clear from the algorithm that I'm going to show you, because maybe you don't know that, you don't know the literature on that, but there are a wealth of literature on sorting on partially ordered sets. So if you're familiar with discrete mathematics or theoretical computer science, there has been a bunch of work in the 80s about sorting things or partially sorting things, and it's directly related to the problem that I'm going to talk to you about now, or the algorithm. So here is the formal setting. Here in the dually Bandits, the way the information is encoded between two arms is just that if you pull two arms, I and j, then you have the probability of I winning over j that is given by 1/2 over 1/2 plus a gamma. The gamma is going to tell you whether I is better than j. And the other thing is that when you do bandit, you use bandit problems, is that you don't have access to this probability, or you don't have access to gamma. The only way you can have some information about gamma is to pull the arms, and that's the way you're going to know whether I is better than j. And on posets, you have this problem, which is that, so these are another pair of films, of movies, but you have some of the arms or some of the movies that cannot be compared. For instance, the two movies that I've shown here. This is just to set the problem. The structure, the algebraic structure that I'm going to work with is what is called a poset. So a poset has this property. It's reflexive, asymmetric, transitive, so it's a set equipped with some order, and the only thing to look at is the graph on the right part. So the arrow say that if there is an arrow between G and B, it just says that G is better than B. And here you can see that you can say that A is better than B, A is better than D, but there is no way to directly compare B and D. So if you work with lattices or tries, you know that you have usually this kind of structure where you have subsets of elements that cannot be compared to each other, knowing that if you work with lattices, the order that you use is inclusion. The problem that we have here, and I'm not going to talk a lot about that, is that sometimes in the problem of dueling bandits on posets is you have the problem of indistinguishability, which says that you cannot say, it's very difficult to say apart the situations where two movies are from the same category, or they can be compared but they have almost the same value, and the situation where you don't know whether, so the idea is just you're going to pull arms, pairs of arms, and sometimes one of the arms is going to win, the other is going to win, and if the probability of winning is almost 0.5, you don't know whether it is because the two arms are comparable or and have the same value, or whether they are not comparable. So these are big problems, the big problem that we have, and in order to solve this problem, we're going to use something, and I'm not going to talk a lot about that, but something that is called decoys. That's something that is coming from psychology, and that we were able to input in our framework when we work with hidden posets. That is, we don't have the information about the fact that the poset is known or not. But I'm not going to talk a lot about that because it's very technical. So the contribution is just that. So this is the one slide, which is not very, actually there are two slides. The other one is even uglier. But here, on the right, you have the algorithm to find the best arms. It's just, you know, when you do sorting things, you have a lot of different ways to sort arrays. You can use quick sort, you can use bubble sort if the first time you sort something, and you have all the sorting situation where you use pivot points. So you use pivot, and you're going to use a pivot, and you're going to say all the values that are larger than this pivot, I'm going to put them on the right and the other on the left, and you're going to do that a lot of times. And the idea has been carried over to the situation of posets by many people in the 80s. And what we just did is to put a little salt on that and a little spice, and to say we can do it even though we don't have a precise information on whether a value is larger than a poset or not, than a pivot or not. So it requires us to carefully say how many times we have to pull pairs of arms in order to decide whether one arm is better than the other. But otherwise, okay, I don't have time to explain you that, but we are going to take pivots, and we are going to compare some of the we are going to have a set of pivots, and we are going to have all the remaining arms in the partially ordered sets, and we're going to take one of the non-pivot point and compare it to all the pivots. And depending on the result of this comparison, we're going to discard some of the pivots, or we're going to replace some of them. And at the end, we can retrieve the fact that the best set of the set of best alternatives is made of G, A, and F. We did some experiments on the problem of movie recommendation, and the only thing that is very important to see is that we had two different ways of trying to find the best movies. The first line is our algorithm. The second one is a classical Bandit algorithm that is going to recommend you some movies. And there are not that many differences, but the important thing is that here, this is a classical algorithm, and it puts two movies from the same genre. And the thing is, with our approach, we are able to have more diversity, and this is more a Pareto front, meaning that here, actually, if you really look at that, if you look at the grades, you can compare those two guys. Here, we cannot compare any of the two guys. They are all from different genres, and this was calculated automatically by our algorithm. All right, so this is the thing that is important, that we were able to find all the best alternatives, and the property of the alternatives is that they cannot compare it to each other. So we have what is called the Pareto front. All right, so the conclusion, so we are going to work on contextual versions of the problem, because here it's very simple. It's a very simple model, meaning that we don't take into account some features about the movies. We just take into account the grades, or the fact that one movie is better than the other. And this is actually a small part of a long-term project that I have with colleagues from Marseille or from Criteo, to see how discrete structures can be used in machine learning, because this is something that has been left apart since the advent of all the optimization things and the continuous mathematics things. So this is something that I want to work on together with something that I found very interesting about all the hardware things and in machine learning. Okay, so that's it. I just have 10 seconds left. Thank you.